For our final lecture video on waves, we're going to talk about a specific concept that applies to light waves known as polarization. We'll talk about how the math works in polarization, but we'll also get into the details of some pretty interesting applications that polarization allows for. Before we can really get into that though, let's do a review on the nature of light as a wave. We call light a transverse wave because there are oscillations that are perpendicular to the direction of motion. Note that this is different than a sound wave. Sound waves, we said, were longitudinal waves, where the vibrations of the molecules were parallel to the direction of motion. A sound wave cannot be polarized, but a light wave can, and it has to do with this transverse nature. Now, if you were to imagine this transverse wave as a rope, that you're sending pulses of this wave down the rope, these flags are oscillating up and down as the wave moves from the hand to the doorknob. Now, if you were to imagine that you are in the perspective of this doorknob and watching this wave come at you, it might look something like this, that there's oscillations going up and down, but we see that these oscillations are happening in the vertical plane here, this linear coming at you sort of thing. Well, that isn't really the whole story when we talk about light. That's a really simple concept to think about for like a rope, but when we talk about light waves, that is not the only perpendicular direction to the direction of motion. This would also be perpendicular to the direction of the motion because the motion is coming at you. You're the doorknob. So oscillating sideways would also be perpendicular. Oscillating in these diagonals would also be perpendicular. So all of these for light are happening at exactly the same time. We call this unpolarized light. If there's light coming from the sun, it is unpolarized. It is oscillating in all these dimensions all at once. To polarize that light is going to be to simplify this back down into that simple waveform that's either perfectly vertical or perfectly horizontal or perfectly some angle, but it is only operating in one dimension. Right here in front of me, I've got a little polarizer. This polarizing is just a filter. It looks a little tinted, but other than that, there's not a whole lot of difference that I can see between this and any other piece of transparent plastic. Well, this polarizer takes that unpolarized light, the light that's oscillating in every dimension, and it filters out all of the other ones so that there's just one oscillation going in one direction. If I hold this up to the camera, you'll still be able to see through it, but it's slightly tinted. That tinting is about 50% of the intensity of the original light. It probably doesn't look that way exactly. My camera probably adjusts according to the lighting that it's given. But 50% of the light intensity that makes it, or starts on one side, makes it all the way through. And if you think of it, what it's doing is it's filtering out all of, if I've got this vertically polarized, it's filtering out all of the horizontally polarized light, which will take out 50% of the options. Now, I know there were lots of different options. It wasn't just vertical and horizontal, but all of these can be broken down into vertical and horizontal components. So if you take out all the horizontals, you end up with 50% of the overall light intensity that you had to begin with. Now, to conceptually understand what's happening here, it takes a little bit of a mental leap because you can't see light waves. And, well, you can't see the oscillations going like that in light waves. And you can't see exactly what's going on, at least with your naked eye, in this polarized filter. So a great conceptual model to think about is a picket fence or a crate, as shown here. If I've got a wave going in a rope that this is vertically oscillating wave, it is going to easily pass through a vertically slotted picket fence or a crate. If I set up another polarized filter or another crate picket fence that's also perpendicular, it's not going to have any problem to go through that as well. So one filter can filter out all of the horizontal light, so I'm only left with vertical polarization light. And then I can set up another filter vertically, and it passes through that as well. So that doesn't change the intensity at all. From one filter to two filters because both of them are set up perpendicular, are set up vertically in this case. If I set one of them, so instead of being vertical, it's now horizontally polarized, I'm going to see a very different result, because that vertical polarization sets up all the waves to be up and down. But then if the next one is horizontal, it's not going to be able to pass through that second polarizing filter. So what's going to happen here is if I set this up first to be vertical, and then I just rotate it. So I don't know how easy it's going to be to see. Let's do it this way. So now you can still see my eye. If I rotate this, you can see that that blacks out all of the light. So just by rotating this filter, I can very dramatically change the amount of light that makes it through. If I set this up right on the camera and I rotate it now, I can essentially cut out all light entirely for making it through, just because I have changed the orientation of these two filters. So obviously there were some instances in between, right? Like I could start out both of these going vertically and then start to rotate so that one becomes horizontal, and it's dimming. It's not like shut off, no light anymore. There's a gradient there. So let's talk about how we can define that gradient. Well, it's going to be mathematically related through a mathematical model known as Malices Law. Malices Law is talking about light going through a polarizer and then through another polarized filter known as an analyzer. This is the equation that we're going to be dealing with, and let's define what these different variables are talking about. I, in this case, is the intensity of light that is experienced after it goes through both. I naught is the intensity of light that it has before it makes it through the analyzer. So really, Malice's law is looking at how does it change between the first filters, between the filters, and then after it goes to that second filter. Cosine theta, or cosine squared theta, theta here is the angle between filters. This, for those of you who are less familiar with what a squared cosine would be the same thing in your calculator as just typing in the cosine of theta and then squaring that whole quantity. It's just another notation, another way to write that. This equation shows up in your data booklet under the 4.3 wave characteristics for IB. I is equal to I naught cosine squared theta. So I want to note, we had talked about if I put one of these up here, it's going to cut the intensity in half. Going from unpolarized light to polarized light is always going to give me this 50% loss. But from there, that's where Malice's law comes in to help you define from that leftover light, that 50% polarized light, this is how much is lost through a subsequent filter. So this really only applies if your light is already polarized, and then again, to get it polarized, you have to lose 50% of the light if you're starting with unpolarized light. Here's a sample problem. The intensity of a plane polarized light at 40 degrees to the vertical is I naught. After passing through an analyzer at 60 degrees to the vertical, what is the intensity measured? So here, we're not ever dealing with perfectly vertical light. Instead, we're starting with light that's already been polarized. It was polarized at 40 degrees to the vertical. Now we're adding an extra filter that's at 60 degrees to the vertical. All we really care about, though, is the difference between these two. If instead that first one was perfectly vertical, then the other one would only be 20 degrees from the vertical. We'd just be shifting them both 40. So if we're talking what theta is in this equation, it's the difference between them. 60 minus 40, our difference is 20 degrees. And I want to know what's the intensity measured after it makes it through that second one if the initial polarized light was I naught. Since it's already polarized, we don't have to worry about that 50% loss. We can just plug it into our equation. I naught times the cosine squared of 20 is 0.883 times I naught. So cosine squared of 20 is basically giving you 88.3% of that original intensity. This equation makes sense as well if this is perfectly perpendicular. From one to the next, we would have a angle difference of 90 degrees, and the cosine of 90 degrees is always going to give you 0. So that will basically mean that your intensity is fully cut off, that there is no light that makes it through if it's a 90-degree angle. So another example, kind of going along with that idea, polarized light of intensity I naught is incident on a polarizing filter. The angle between the polarization of the incident light and the transmission plane is 0 or is theta. Which graph shows the intensity I of the light transmitted through the polarizer as it varies with theta? So basically what it's asking you here is you start with these two polarizers exactly in the same direction, and then you just slowly rotate one of them so that it dims the light until it hits 90 degrees. Notice at that 90 degrees, we are at 0. So I want a graph here that represents the fact that if these polarized filters are at 90 degrees to each other, the intensity will be 0. And then what's left over is just finding one that has a cosine squared shape to it. So looking at these graphs, which one of these would give you a cosine squared shape? Well, it's this one here, or this one, but this one is the one that gives you 0 intensity at 90 degrees. So we're going to go with this bottom right. Now let's look at one calculation before we get into some applications here. After passing through one polarized filter, the intensity of a vertically polarized light is 60 watts per square meter. That is a unit of intensity that we'll get at later on in this year. What is the angle of the analyzer relative to the vertical if the intensity observed is 20 watts per square meter? So basically what this is saying is we have passed this unpolarized light through a polarizer, and what we're left with is polarized light that has an intensity of 60 watts per square meter. Then after the analyzer, we're going to get 20 watts per square meter. So I want to figure out what angle would allow that to happen. Again, this is our equation. You could write it either way, cosine squared theta or cosine of theta squared. And plugging in what I've got, my final intensity, this I, is 20, and the initial intensity of the polarized light was 60. So that means I can divide both sides by 60. So I get 20 over 60 and take the square root. And then eventually take the inverse cosine. And we'll take care of that cosine right now. There we go. So taking out that cosine here, because we took the inverse cosine of 20 over 60 with the square root, we can calculate what the angle of that's going to have to be. So go ahead and plug that into your calculator to figure out what angle would give you a loss from 60 down to 20. In this case, your angle in degree mode should be about 54.7 degrees. Now, then talking about what we've talked about so far, if our polarized light here was 60 watts per square meter, what was the intensity of the unpolarized light before it made it through that first polarizer? We've talked up until this time that a single polarizer is going to cut it by half. That means that if it ended up at 60, it had to have started with 120 watts per square meter. So the journey here is 120 gets cut down to 60, gets cut down again to 20. Now, this isn't the only way to polarize light, sending it through a polarizer. This actually happens in nature quite often. That reflections off of a horizontal surface become horizontally polarized. If you are looking out on the water, like a lake surface, you're going to see the glare off of that water coming at you. That actually has a horizontal polarization. It's coming at you in the horizontal plane, which means that if you want to cut out that glare, all you need is a single polarizer to do that. You may have heard of polarized sunglasses. They're usually a little bit more expensive than your typical sunglasses that are just tinted. These polarized sunglasses, in addition to being tinted, are also polarized so that they're not just dimming the light, they're cutting out all horizontally polarized light, which means you don't see the glare anymore. If you've used polarized sunglasses, sometimes it's so you can see into the water if you're a fisherman, or if you're driving on the road, it's a way of cutting out the glare that you might have coming off the road. Another application of polarization is 3D movies. This is one of my favorite applications of this. You've maybe been to a movie where you've gotten 3D glasses like this. Well, the concept here to make something 3D is you just need to have the two eyes experience different images. That's why you see in 3D in general, because each eye has a slightly different image and slightly different perspective, and your brain stitches that together into a 3D image. Well, there are three main types of 3D glasses. The first, the oldest version is a red cyan. So you basically just tint the image and then use tinted lenses so that each eye can only see one part of that. You could have polarized glasses like these ones here. We'll talk about how those work. Or you could have active shutter glasses, which use polarization to just shut off one eye at a time in synchronization with the images that are flashing on the screen. This middle one here, these polarized glasses, work so that each eye receives a slightly different image because each lens is polarized in a different direction. So all you need to do is project a different polarized, or two different polarized images on the screen so that when they bounce off into your eyes, each one gets cut off by the corresponding lens so that one eye only receives its intended image and the other receives its intended image, and the polarization cuts out the rest of that. Turns out that a similar style of creating an image using polarization is how a lot of screens work. You might see situations like that on a phone. So if I take my phone here, turn up its brightness, so you can see that I can change my phone's image using a polarized filter. I can cut that out because there is polarization in the creation of this image. Well, there is another example using screens like a computer monitor that you can actually create what's known as a magic screen. So to introduce that, I'm going to pass it off to the second episode of Bedtime Science. Welcome back to another episode of Bedtime Science. This episode is called The Magic Screen. You might notice that Callie and I are wearing special glasses. What kind of glasses do you have? They are black glasses, and these glasses are from a 3D movie. The reason we're wearing these is today we're talking about something called polarized light. Light, if it comes from the sun or other sources, is in every direction all at once. But a polarized filter, you can kind of imagine like a bunch of vertical or horizontal lines that only let some of the light through. Callie, can you show us what letting some of the light through would look like? Can you do this with your hand? So if we have light that only comes vertical or only comes side to side, then we can do some interesting things with that light. This magic screen here is just a normal computer monitor that's actually playing one of Callie's favorite shows right now. We can't see it because I took off the polarizing filter. This is the final component that lets you turn the light that's going on here into a colorful picture. If I put this on the screen, Callie, do you know what show that is?
Baby Shark.
Yeah, they're playing Baby Shark. Now, these sunglasses aren't actually sunglasses at all. Yeah, these sunglasses are making it so that we can see the show as well, because they have a polarizing filter in it as well. Just to show you, I'm going to take off my sunglasses and I'm going to let you watch the show. Notice how the only difference is that you're looking at it with or without a filter. And the reason that works is because we are taking the light and we are making it go in one direction the way we want it to. This works in a lot of different technology, from 3D movies to computer monitors to some TVs as well. All right, Callie, should we keep watching our show?
Yeah.
All right, you better put on your sunglasses.
No.
Can you see it without your glasses?
No.
Join us next time on Bedtime Science. Callie, can you say bye?
Bye.
All right, so our final takeaways for this lesson is you should be able to describe the transformation that takes place when unpolarized light becomes polarized. You should also be able to describe the interaction between two polarized filters and what the angle in between them is going to do to the overall light intensity. And you should be able to use Malices Law to calculate the change in intensity when passing through two polarized filters at some angle difference, using that I naught times the cosine squared of theta.